What if I told you we could make AI models smaller, faster, and smarter all at the same time? Or that we could get them to plan and reason like never before? And what if the key to better AI oversight was understanding how models fail together? Sounds like science fiction, right? Well, buckle up because it's all happening now.
Welcome to AI by AI. Today we're diving deep into some cutting-edge research that's pushing the boundaries of what's possible with large language models. First up, we'll explore CodeSteer, a method for guiding LLMs to be better at code and text generation using symbolic computing. Think of it as giving your AI a super-powered calculator. Then we're tackling Quest, a way to train LLMs with super low precision, making them smaller and faster without sacrificing accuracy. After that, we'll see how we can use test-time compute scaling to help LLMs generate plans, even when they haven't been specifically trained for it. We'll also be covering R, a new prompting method that helps LLMs answer questions more accurately by breaking them down step by step. Finally, we'll wrap up with CAPA, a metric that helps us understand how similar different LLMs are, especially when they make mistakes, crucial for AI safety and oversight. So stick around, it's going to be a wild ride.
All right, let's dive into this CodeSteer paper. It's all about making large language models, or LLMs, better at using both text and code to solve problems. The core idea is to guide these models to decide when to use regular text-based reasoning and when to generate and execute code. Why is this important?
Because LLMs are great at understanding language, but they often struggle with tasks that require precise calculations, symbolic manipulation, or complex algorithms. That's where code comes in. Think of it like this. Text is for understanding the question, and code is for crunching the numbers and getting the right answer.
Exactly. The paper points out that many existing benchmarks have tasks that can be completely solved with code, so the challenge is to get the LLM to recognize when code is the best tool for the job. They introduce something called CodeSteer, which acts like an assistant to guide the LLM.
So, CodeSteer is like a little helper that nudges the bigger LLM in the right direction? How does it work?
It's fine-tuned to guide the LLM through multiple rounds of interaction. It decides whether to use text or code, and if code is chosen, it helps refine the code generation process. They use a smaller model, Llama 3.8b, as the CodeSteer assistant to guide larger models like GPT-4o.
Okay, so it's not just a one-shot thing, it's an iterative process. That makes sense. But how do they know if CodeSteer is actually working?
They created a benchmark called SymBench, which includes 37 symbolic tasks with adjustable complexity. These tasks cover areas like mathematics, spatial reasoning, logic, and planning. They then fine-tuned Llama 3.8b using a multi-round supervised fine-tuning, SFT, and direct preference optimization, DPO.
SFT and DPO, those are mouthfuls. Can you break those down?
Sure. SFT, or supervised fine-tuning, is like teaching the model by showing it examples of how to guide the task LLM. DPO, or direct preference optimization, is about teaching the model which guidance strategies are better than others. It's like giving it a thumbs up or thumbs down on different approaches.
Got it. So they're training CodeSteer to be a good guide by showing it examples and giving it feedback on its choices. What were the results on SymBench?
Massive improvements. When they used CodeSteer to guide GPT-4o, the average performance score jumped from 53.3 to 86.4. It even outperformed other top-tier LLMs like OpenAI's O1 and DeepSeek R1. Plus, CodeSteer showed good generalizability, meaning it also improved the performance of other models like Claude and Mistral.
Wow, that's a significant boost. So CodeSteer isn't just good for one specific model, it can help others too. What makes CodeSteer so effective?
A couple of things. First, they use a symbolic checker to evaluate the complexity and efficiency of the generated code. This helps CodeSteer avoid code that's just hard-coded answers instead of actual symbolic computation. Second, they use a self-answer checker where the LLM generates and executes code to verify its own answer. This is especially useful for reasoning and planning tasks.
So the checkers are like quality control, making sure the code is legit and the answers are correct. That's the paper. Also mentions some challenges in steering LLMs between code and text. What are the main hurdles?
One big challenge is deciding whether code or text is simpler for a given task. It depends on the task type, complexity, and the LLM's capabilities. Another issue is that LLMs sometimes generate code that looks like code but is really just text-like scripts that hardcode the answer. That defeats the purpose of using code for symbolic computation.
Right. You want the LLM to actually solve the problem with code, not just pretend to. It's like showing your work in math class. What about the multi-round aspect of CodeSteer? How does that improve things?
The multi-round interaction allows CodeSteer to dynamically adapt its guidance. For example, it might start with code but switch to text if it encounters issues, or vice versa. It also refines the guidance in subsequent rounds based on the task LLM's previous answers. They found that the final 2 rounds of guidance are the most influential, so they weighted those rounds more heavily during training.
That makes sense. It's like having a conversation where you adjust your advice based on the other person's responses. The paper also talks about something called the multi-round gradient cancellation issue. What's that about?
In multi-round training, the model gets feedback from each round. But sometimes different paths can lead to the same correct answer. This can cause the model to get confused about which path is the best one, especially in the early rounds. That's why they augmented the dataset by emphasizing the final 2 rounds, where the task LLM produces new answers.
So they're focusing the training on the rounds that have the biggest impact on the final answer. Smart. What about the cost of using CodeSteer? Does it require a lot more computing power or tokens?
It does use more tokens than some baseline methods because of the multi-round interactions. However, it's faster than some other approaches like those that rely solely on textual reasoning. Plus, they point out that the runtime can be significantly reduced with hardware and system optimizations. They even showed that running CodeSteer LLM on 4 H100 GPUs instead of 1 decreased the average runtime.
So there's a trade-off between token usage and runtime, but the performance gains seem to outweigh the costs. It's interesting that they used a smaller model, Llama 3.8b, for CodeSteer. Why not use a larger model?
They argue that focusing on guidance allows them to use a smaller model, which reduces task complexity and data space requirements. The CodeSteer LLM primarily serves as the guidance generator for task LLM rather than directly generating answers, summarizing, or selecting on multiple answers. This design choice accounts for the limitations of the open-source LLM they use compared to the more capable closed-source LLM that supports task LLM.
That makes sense. It's like having a specialized tool for a specific job. So overall, CodeSteer seems like a promising approach for improving LLM's ability to leverage both text and code. It's all about guiding the model to make smarter choices about when to use which tool.
All right, let's dive into this paper. Quest Stable Training of LLMs with 1-bit weights and activations. The core idea here is to make large language models, or LLMs, more efficient by using really low precision numbers during training. We're talking about 1-bit weights and activations.
1 bit? That sounds incredibly aggressive. For those not familiar, can you break down what weights and activations are in the context of LLMs and why reducing their precision matters?
Absolutely. Think of weights as the parameters the model learns. They're the connections between neurons that determine how strongly one neuron influences another. Activations are the outputs of those neurons. Now, normally these are stored as 16-bit or even 32-bit floating point numbers. Reducing that to 1 bit dramatically shrinks the model size and speeds up computations. It's all about making these massive models more manageable and faster to run, especially on hardware with limited resources.
Okay, so the paper mentions Quantization-Aware Training, or QAT. What's that, and why is it important in this context?
QAT is where you train the model from the get-go using these low-precision numbers. It's different from post-training quantization, where you train a model in full precision and then compress it afterward. The idea with Q is that by training with low precision from the start, the model can learn to compensate for the limitations and maintain accuracy. The paper points out that previous research suggested 8-bit precision was the sweet spot for QAT, but Quest aims to push that boundary way further.
So, what's the big deal with Quest? What makes it different and allows it to go down to 1 bit?
Quest tackles 2 key challenges in QAT. First, it improves how we convert the normal, continuous distributions of weights and activations into these discrete quantized values. They do this using something called Hadamard normalization and MSE optimal fitting. Basically, they're trying to find the best way to represent the original data with these limited number of bits.
Hadamard normalization? That sounds fancy. Can you give us the elevator pitch on what that does?
Think of it as a way to reshape the data distribution to make it easier to quantize. The paper mentions that weight and activation distributions in LLMs tend to be sub-Gaussian with long tails. The Hadamard transform helps make these distributions closer to Gaussian, which is easier to handle with quantization. It's like pre-processing the data to make it more quantization-friendly.
Got it. So better data preparation for quantization. What's the second key improvement they made?
The second part is all about how they estimate the gradients during training. Remember, we're using low-precision numbers in the forward pass, but we need to update the weights accurately. They introduce a trust gradient estimator that tries to minimize the difference between the noisy gradient computed with quantized values and the true gradient we'd get with full precision.
A trust gradient estimator. That sounds like it's trying to be smart about which gradients to trust. How does it work?
Exactly. The intuition is that if a weight or activation has a large quantization error, meaning the quantized value is very different from the original, then the gradient calculated from that quantized value might be unreliable. So the trust estimator reduces the importance of those gradients, focusing on the components where the quantization is more accurate.
So it's like saying, I don't fully trust the gradients from these low-precision numbers, so I'll be more cautious with them. Makes sense. The paper mentions a straight-through estimator or STE. What's that and how is Quest different?
STE is a common technique used in Q. It essentially pretends that the quantization operation doesn't exist when calculating gradients. It's a simple way to allow gradients to flow through the network, but it can lead to inaccuracies because it ignores the quantization error. Quest's trust estimator is a more sophisticated approach that tries to account for that error.
Okay, so Quest is smarter about handling the inaccuracies introduced by quantization. What kind of models did they test this on, and what were the results?
They trained llama family models ranging from 30 million to 800 million parameters on the C4 dataset. They found that Quest allowed for stable training even with 1-bit weights and activations, and that models trained with 4-bit precision actually outperformed BF16 models, which use 16-bit floating point numbers of comparable size. That's a huge win in terms of efficiency.
That's pretty impressive. So, smaller models with better accuracy. The paper also talks about Pareto optimal frontier. What does that mean in this context?
The Pareto optimal frontier represents the best possible trade-off between accuracy and model size, or inference cost. A model on the Pareto frontier is the most accurate you can get for a given size, or the smallest you can get for a given accuracy. Quest shifts this frontier, meaning it allows you to achieve better accuracy with smaller models compared to previous methods.
Got it. Best bang for your buck, so to speak. Did they look at how well these Quest-trained models actually run on hardware?
Yes, they developed custom GPU kernels to efficiently execute the models produced by Quest. They showed that using these kernels with 4-bit precision can lead to significant speedups compared to using standard 16-bit matrix multiplications. They saw per-layer speedups of up to 3.9x on a proportionally scaled 7B parameter model.
That's a substantial speedup. So to summarize, Quest is a new quantization-aware training method that uses Hadamard normalization and a trust gradient estimator to enable stable training of LLMs with extremely low precision, down to 1 bit. It achieves better accuracy with smaller models and provides significant inference speedups. What are the limitations and future directions mentioned in the paper?
The authors acknowledge that they've only tested Quest on models up to 800 million parameters, so it's important to see how it scales to much larger models. They also focused on decoder-only architectures, so extending it to encoder-decoder models is another area for future work. Overall, Quest seems like a promising step towards making LLMs more accessible and efficient. All right, let's dive into this paper on generating symbolic world models using large language models, or LLMs. The core idea is to use LLMs to create planning domain definition language, or PDDL domains. Why PDDL, you ask? Well, it's a formal language that precisely describes states and actions, which helps in planning complex tasks.
Exactly. Think of PDDL as a super organized way to tell a computer how the world works. Instead of vague natural language, PDDL uses logic to define states like the robot is at position A, and actions like move the block from A to B. This makes it easier to verify plans and ensure they follow the rules.
But here's the catch. LLMs aren't naturally great at generating PDDL. There's not a ton of PDDL training data out there, and it's tricky to maintain logical consistency. So the authors propose a clever solution: scale up the test time computation of LLMs. Basically, give the LLM more chances to think and refine its answers.
They introduce a two-step process. First, they use best-of-n sampling, or BOEN. The LLM generates multiple PDDL domains, and they pick the best one as a starting point. It's like brainstorming a bunch of ideas and then choosing the most promising one.
Right, BOEN helps explore the solution space and find a decent initial solution, but it doesn't refine that solution. That's where the second step comes in: instance verbalized machine learning, or IVML. This is where things get really interesting.
IVML is like having the LLM critique its own work and then improve it. It uses two LLMs: an optimizer that evaluates the PDDL domain and provides feedback, and a learner that uses that feedback to refine the PDDL code. This process repeats, iteratively eliminating errors and inconsistencies.
So the optimizer LLM essentially acts as a verifier, checking if the PDDL domain makes sense and aligns with the original problem description. It generates critiques which serve as verbalized gradients, guiding the learner LLM to make better PDDL domains.
And the cool thing is, this whole process happens at test time, meaning no additional training data is needed. They're just leveraging the existing knowledge and reasoning abilities of the LLM, but in a smarter way.
Exactly. They're scaling the computation, not the model itself. This is a key contribution. They show that this approach significantly outperforms just using an LLM directly, especially on complex planning tasks.
They tested their method on a bunch of international planning competition benchmarks, which are known for being challenging. They looked at two tasks: NL2 domain, which is converting natural language descriptions into PDDL domains, and PROB2 domain, which is deriving PDDL domains from PDDL problems.
And the results are impressive. Using Quen 2.5 Coder 7b as the base model, they achieved state-of-the-art performance, with success rates over 85% on NL2 domain and 71% on PROB2 domain. That's a huge jump compared to just using an LLM like O1 Mini directly.
It's worth noting that code-oriented LLMs, like Quen 2.5 Coder, tend to perform better than general-purpose LLMs on this task. This makes sense, since they're trained on code datasets that teach them about type systems and predicate logic, which are essential for PDDL.
The paper also dives into the convergence behavior of BOEN and IVML. They found that BOEN sampling has diminishing returns after a certain point. You get better results up to a point, but then it plateaus. IVML, on the other hand, shows monotonic improvement as you increase the number of iterations.
That makes sense. BOEN is good for exploring the solution space, but IVML is better at exploiting the best solutions and refining them. It's a great combination of exploration and exploitation.
They also did an ablation study to see how different initialization strategies affect IVML's performance. They compared single-pass sampling to BOEN 8, which is BOEN with 8 candidate solutions. And unsurprisingly, BOEN 8 helps IVML converge faster and achieve better results.
It's like giving IVML a head start. Instead of starting from scratch, it starts with a pretty good solution that BOEN has already identified.
One interesting finding is that even with IVML and BOEN, weaker LLMs still struggle. They tried it with LLama 3.1 Instruct 8b, which had a 0 success rate in the main experiment. IVML with BOEN 8 did improve its performance a bit, but it was still far behind the stronger models. This suggests that there's a limit to how much you can improve a model through test time scaling if it lacks the fundamental knowledge and reasoning abilities.
Yeah, you can't polish a rock into a diamond. You need a certain level of inherent capability to start with.
The paper also compares their PDDL-based approach to using LLMs directly as planners, which they call LLM as planner methods. And the results are pretty clear. PDDL abstraction leads to more robust planning.
LLMs as planners often hallucinate, violate rules, and make incorrect state transition estimations. They treat planning as a text completion problem rather than a logical reasoning problem. PDDL forces them to be more precise and structured.
Exactly. By generating PDDL domains, they're shifting the role of LLMs from being planners to being world model generators. And then they can use classical search algorithms like A-STY to find optimal plans within that world model.
So to wrap it up, this paper presents a really clever way to leverage LLMs for complex planning tasks. By scaling up test time computation and using PDDL as a formal abstraction, they can overcome the limitations of LLMs and achieve state-of-the-art performance. It's a great example of how to combine the strengths of LLMs with more traditional AI techniques.
Definitely. It's not about replacing classical planning with LLMs, but about using LLMs to enhance classical planning. And that's a powerful combination. Okay, let's dive into this paper about improving question answering with large language models. It's called ARR, which stands for Analyzing, Retrieving, and Reasoning.
Sounds interesting. So what's the core idea here?
Basically, the authors argue that when LLMs answer questions, they should explicitly go through these 3 steps. First, analyze the intent of the question, then retrieve relevant information, and finally, reason step by step to get the answer.
That makes sense. It's like how we humans approach problem solving. But how is this different from what LLMs already do?
Well, the standard approach is often something called chain of thought or CoT prompting. It's where you tell the model to think step by step. But the authors argue that this is too vague. ARR provides more specific guidance.
So CoT is like saying be smart, while ARR is like giving a detailed checklist. Got it. How do they implement this ARR?
They use a specific answer trigger sentence. Instead of just saying answer, they say, let's analyze the intent of the question, find relevant information, and answer the question with step-by-step reasoning.
Simple enough. What kind of questions did they test this on?
They used a bunch of multiple-choice question-answering data sets. These covered everything from reading comprehension and common-sense reasoning to world knowledge and multitask understanding.
So a pretty broad range. What were the results? Did ARR actually improve performance?
Yes, it did. Across the board, ARR consistently outperformed the baseline, which had no specific trigger sentence, and even the zero-shot CoT method. They saw a significant improvement, like a 4% increase on average.
That's a solid boost. Did they try to figure out which part of ARR was most helpful?
Yep, they did an ablation study. They tested each component, analyzing, retrieving, and reasoning separately, and they found that each one individually outperformed the baseline and CoT.
Interesting. So all 3 are important. Was there one that stood out?
Interestingly, the analyzing only setting gave the biggest performance gain on average. This suggests that understanding the question's intent is super crucial.
That's not too surprising. If you don't understand the question, you're likely to go down the wrong path. Did they look at specific examples to see where ARR made a difference?
They did. They presented case studies where the baseline and CoT methods failed due to things like misunderstanding the question or using context incorrectly. ARR, because of its intent analysis, was able to stay on track and get the right answer.
Okay, so it works in controlled experiments. But how well does it generalize to different models and situations?
That's what they tested next. They ran experiments with different model sizes, different LLM architectures, different generation temperatures, and even in few-shot learning scenarios.
And the verdict?
ARR held up pretty well. It consistently outperformed the alternatives across these different settings. This suggests that it's a robust and adaptable method.
That's great. So to recap, ARR is a simple but effective way to improve question answering by explicitly prompting LLMs to analyze the question, retrieve relevant information, and reason step by step. And it seems to work across a variety of models and tasks.
Exactly. It's a nice, intuitive approach that seems to tap into the way humans solve problems.
Are there any limitations to this study?
The authors mentioned that they only explored one specific phrasing of the ARR prompt. There might be other ways to phrase it that could work even better. Also, they primarily focused on open-source LLMs with fewer than 8 billion parameters. They suggest that ARR could be even more effective with larger models.
Good points. It would be interesting to see how ARR scales with the really massive models. Anything else?
They also noticed that the generated reasoning can sometimes be repetitive. They suggest that a dynamic stopping strategy or some post-processing to remove redundancies could further improve performance and reduce computational cost.
Overall, it sounds like a promising approach. I'm curious to see how ARR is adopted and refined in future research.
Me too. It's a great example of how a simple, well-designed prompt can significantly improve the reasoning abilities of large language models. Okay, let's dive into this paper. Great models think alike, and this undermines AI oversight. The core idea is that as language models get better, they also start making similar kinds of mistakes, which could be a big problem for how we oversee AI systems.
Right, so the abstract introduces this Chance Adjusted Probabilistic Agreement, or CAPA. What exactly is CAPA and why is it important?
CAPA is a new way to measure how similar two language models are, focusing on their mistakes. It's not just about whether they agree, but whether they agree more than you'd expect by chance, given how accurate they are. It also considers the probabilities the models assign to different answers, not just the single top prediction. This is crucial because it helps us quantify functional similarity between models.
So it's like saying two models are truly similar if they're making the same kinds of errors, even when they're generally pretty good. How does this compare to other ways of measuring model similarity?
Exactly. The paper distinguishes between representational and functional similarity. Representational similarity looks at the internal workings of the models, the weights and activations. Functional similarity, which CAPA falls under, looks at the input-output behavior. Functional similarity is more practical because it works even if you don't have access to the model's internals, like with an API. Plus, it's more interpretable because it deals with data samples directly.
Got it. So CAPA is a functional similarity metric. What were the key findings using CAPA?
The paper highlights three main findings. First, when using one language model to judge another, LLM as a judge, the judge tends to favor models that are similar to itself. It's like a hiring manager preferring candidates with similar backgrounds, affinity bias. Second, when training a strong model using annotations from a weaker model, you get better results if the two models are dissimilar. This suggests that complementary knowledge between the models is key for weak to strong generalization.
That makes sense. If the models are too similar, the weaker one isn't really teaching the stronger one anything new. What's the third finding?
The third, and perhaps most concerning finding, is that as language models become more capable, their mistakes become more correlated. This means they're developing common blind spots, which is a big problem for AI oversight. If we're relying on AI to supervise AI, but all the AIs are making the same mistakes, we're in trouble.
Okay, let's break that down. So AI oversight is basically using AI to evaluate and supervise other AI, right? Why is this becoming more popular?
Precisely. It's becoming more popular because as models get more complex, it's harder for humans to keep up. Getting human preferences or expert annotations is slow and expensive. So using language models to automate annotation and scoring seems like an attractive alternative.
But if the models are making similar mistakes, that undermines the whole point of having AI oversight. It's like having a team of auditors who all miss the same red flags. How does CAPA help us understand this?
CAPA allows us to quantify this similarity in mistakes. The paper builds on an existing metric called error consistency, which measures the overlap in mistakes between two models. But CAPA improves on this by considering different kinds of mistakes and incorporating the probabilities the models assign to their predictions. This gives us a more nuanced picture of how similar the models really are.
Can you give an example of how CAPA captures something that error consistency might miss?
Sure. Imagine two models both make the wrong prediction on a question, but one model was really confident in its wrong answer, while the other was just guessing. Error consistency would treat these as the same kind of mistake. CAPA, however, would recognize that the first model's mistake is more significant, indicating a deeper similarity in how the models are processing the information.
So CAPA is more sensitive to the degree of agreement, not just the binary correct-incorrect. How is CAPA actually calculated?
The CAPA calculation involves two key components: observed agreement, CPIPS, and chance agreement, CPEXP. Observed agreement is the probability that the models would agree if you sampled their predictions based on the likelihoods they assign to each option. Chance agreement is the agreement you'd expect from two independent models, given their accuracies. CAPA then adjusts for this chance agreement, similar to Cohen's CAPA, to give a measure of excess agreement beyond what's expected.
Okay, so it's normalizing for accuracy. That makes sense. What about the LLM as a judge finding? How did they demonstrate that affinity bias?
They evaluated a bunch of different language models as judges on a benchmark called MMLU Pro, which tests problem solving across various domains. They had the models answer questions in a free text format, and then the judges had to decide whether the answers were correct or not. They found a significant positive correlation between the judge's score and the similarity, as measured by CAPA, between the judge and the model being evaluated. Even after controlling for the actual accuracy of the models, the similarity still had a significant effect on the judge's score.
So even if a model was objectively better, it would get a lower score from a judge that was dissimilar to it. That's pretty concerning for leaderboards and evaluations that rely on LLM judges.
Exactly. It suggests that we can't just use any language model as a judge and expect a fair evaluation. We need to account for this affinity bias, perhaps by using a diverse set of judges or by correcting for similarity scores.
What about the weak to strong generalization finding? How did they show that dissimilarity leads to better training outcomes?
They followed a setup where a strong, larger model is trained on data annotated by a weaker, smaller model. They found that the performance gains were higher when the weak supervisor and the strong student model were more dissimilar, as measured by CAPA. This suggests that the weaker model is providing some complementary knowledge that the stronger model doesn't already have.
So it's not just about the quantity of data, but the diversity of the knowledge being transferred. How did they tease apart the effects of complementary knowledge from the elicitation effect, where the weak supervisor just helps the strong model unlock its own latent knowledge?
They compared the performance of the weak to strong trained model to a strong elicited model, which was fine-tuned on ground truth annotations. By looking at which model was correct on different subsets of the data, they could disentangle the gains from elicitation versus complementary knowledge transfer. They found that both played a significant role, but that complementary knowledge transfer could actually lead to higher performance than previously estimated, if leveraged effectively.
That's a really interesting finding. It suggests that there's more potential for improvement in weak to strong training than we thought. Now let's get to the concerning part, the increasing similarity of mistakes. How did they demonstrate this?
They collected sample-wise evaluation files for 130 different language models from the OpenLLM leaderboard and binned them into performance percentile ranges. Then, for each model, they computed its mean similarity using CAPA with other models in the same bin, but from different developers. They found a strong positive correlation between model capabilities and CAPA, meaning that as models get better, their mistakes become more similar.
Did they have any theories about why this is happening?
They did some preliminary analysis. They found that the trend is stronger in instruction-tuned models, which suggests that the fine-tuning process might be homogenizing the model's behavior. They also found that the trend wasn't simply due to the models struggling with harder questions. They also looked at whether using different architectures like Mamba could increase diversity, but it didn't seem to be enough on its own.
So it's not just about the architecture, but also about the training data and fine-tuning procedures. What are the potential implications of this trend?
The implications are pretty serious. It could lead to greater affinity bias in LLM judges, lower potential gains from inter-LM training, and undermine the benefits of using diverse model juries. Most concerningly, it suggests that as we rely more on AI oversight, we're also increasing the risk of correlated failures, where all the models make the same mistake at the same time.
That's a really worrying thought. It's like a systemic risk in the AI ecosystem. What are the limitations of this work, and what future research do they suggest?
One limitation is establishing causation. They've shown correlation between similarity and AI oversight outcomes, but it's hard to prove that similarity causes these outcomes. To do that, we'd need ways to make models less similar without harming their capabilities, which is a challenging problem in itself. Another limitation is that CAPA is primarily designed for multiple choice questions. It's harder to develop similarity metrics for free text outputs, which are more common in real-world applications.
So we need better ways to evaluate free text responses and measure similarity in those contexts. What else?
They also suggest exploring the generator-verifier gap, where it's easier to validate a solution than to generate it. Similarity might play a role here, both in terms of stylistic preferences of the generated solutions and in the size of the generator-verifier gap. Finally, they emphasize the safety implications of correlated failures and suggest measuring LM similarity post-intervention to characterize decorrelation in research bets.
Overall, it sounds like this paper raises some really important questions about the future of AI oversight. We can't just assume that more capable models are automatically better supervisors. We need to be mindful of their similarities and differences and develop new tools and techniques to mitigate the risks of correlated failures.
Exactly. The authors hope that the community shifts towards releasing sample-wise model predictions alongside benchmark scores as they enable richer analysis like measuring similarity. It's a call for more transparency and a more nuanced understanding of how these models are behaving. Well, that was quite the journey, from steering LLMs with code to squeezing them into tiny, efficient packages. It's amazing how quickly the field is evolving.
Absolutely. It's fascinating to see how researchers are pushing the boundaries, not just in terms of raw performance, but also in terms of efficiency and safety. That CodeSteer approach, for instance, really highlights the power of combining different AI techniques, leveraging the strengths of both code and text.
And the work on Quest, making models smaller and faster without sacrificing accuracy, is crucial for democratizing access to AI. Imagine running powerful LLMs on your phone or other resource-constrained devices.
Definitely. And let's not forget the insights into planning. The idea of scaling computation at test time rather than just scaling the model itself is a really clever way to tackle complex problems.
It really underscores the importance of smart prompting and guiding the models in the right direction, as we saw with ARR. Sometimes a simple change in how you ask the question can make a huge difference.
But perhaps the most thought-provoking takeaway is the work on CAPA. The idea that models are becoming more similar in their mistakes as they get better is a real wake-up call for AI oversight. We need to be aware of these common blind spots and develop strategies to mitigate the risks.
It's a reminder that AI safety isn't just about preventing malicious use. It's also about understanding the limitations and biases of these systems, even when they seem incredibly capable.
Exactly. It's clear that the future of AI isn't just about building bigger and better models, but about building smarter, more efficient, and more reliable systems that we can trust. And of course, understanding how they might fail.
Here's to more research that helps us get there. Thanks for tuning in, everyone. We'll be back soon with more deep dives into the world of AI.